Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. Last class I discussed the concept of image enhancement. The objective is to improve the visual quality of an image. Today I am going to discuss the concept of image filtering to remove noises. Image filtering operations can be implemented in spatial domain or in frequency domain. In spatial domain, I can manipulate the pixel values directly. So for this, I can consider neighborhood operations. In case of the frequency domain, I can modify the Fourier transform of the image. So first, I have to determine the Fourier transform of the image, and after this, I can do processing in the frequency domain. And after this, I have to do inverse Fourier transformation to get the process image. So before discussing the image filtering concept, I will first discuss some image processing operations. So already you have understood these operations. I am going to explain it again, some of the operations like zooming and some neighborhood operations. So first one is the image enhancement techniques that can be implemented in spatial domain or in frequency domain. In spatial domain, I can operate directly on pixels. So that means I can change the pixel values directly. And in the frequency domain, I can modify the Fourier transform of an image. So this concept already I have explained. And in this case, I have given one example of image enhancement. I have the original image and you can see the enhanced image. And I have considered some geometric operations. So if you see here, gxy is equal to f x plus a comma y plus b. That means gxy, that is the output image, f txy, txy is the transformation for the x coordinate, tyxy, that is the transformation for the y coordinate. And that means I am changing the domain of an image. So if you see here that gxy is equal to f txxy comma tyxy, that is the I am changing the domain of an image. That is the spatial coordinates I am changing. So based on this equation, I can do scaling operation, I can do translation operation, or I can do the operation like the zooming operation. Zooming operation also I can do. The image zooming either magnifies or minifies the input image. So if I consider suppose some transformation tx xy, and in this case suppose x coordinate is divided by c, and if I consider tyxy, the y coordinate is divided by d. So by this transformation I can do zooming in and the zooming out. And in this case I have shown some operations like rotation I can do, and also I can do the scaling. That is, I am changing the domain of an image. And in this case I am showing some neighborhood operation, that is the spatial or the neighborhood operations. So for this I am considering one window. The window is given by wxy, that is the window. And I have the output image. The output image is gxy. Then in this case I am considering the neighborhood pixels for the processing. So if you see this window, this is the window, and corresponding to this center pixel, I am considering the neighborhood pixel, and based on this neighborhood pixels, I can do the processing. That is called the neighborhood operations. I can give one example of the neighborhood operation here. The input image is fij, this is the input image, divided by n, that is the number of neighborhood pixels, and I am considering one window. The window is wxy, that window I am considering, and I am getting the output image. The output image is gxy. So this is one example of neighborhood operations. And I can do some operations between images. So first you can see the addition of two images, the subtraction of two images, that is the gxy is subtracted from fxy. So this is the subtraction operation, multiplication of two images, and you can see the division operation. So in case of the subtraction, that is nothing but the sense detection. Already I have explained in my second class. So it is nothing but the sense detection. If I want to detect the moving regions, then in this case I have to apply the subtraction operation. That is called the sense detection. And in this case you can see that I am doing the addition of number of images. Now because of these operations, the arithmetic operation can produce pixel values outside the range. The range is already, we have the range from 0 to 255, that is mainly from 0 to L minus 1 number of levels I am considering. So arithmetic operation can produce pixel values outside the allowable range. Then in this case what I have to do, I have to convert the values back to the range. The range is from 0 to 255. So I have to do this. And in this case, if I consider the multiplication of an image, suppose the multiplication of fxy by a constant, suppose the constant is c, that is nothing but the scaling. I can do the scaling. Then in this case, by this operation, I can change the brightness of an image. The brightness I can adjust. If the scaling factor is greater than 1, that means in this case the brightness of the image will be more, and a factor less than 1 darkens the image. So I can do the scaling of the image. And similarly in the division also, if I consider fxy divided by some constant, just suppose d, by a factor d, that is very similar to sense detection. That is very similar to sense detection. Now in this case I am considering that how to remove noises based on averaging. So I am considering one image, that is fxy is the noiseless image, and I am considering the noise is nxy, and suppose the gxy is equal to fxy plus nxy. And one consideration I am considering, that is the noise is uncorrelated and has 0 average value. Then in this case if I consider the k number of images, I am taking the average of k number of images. The images, you can see the images is gxy, and I am determining the mean value I am determining, that is the average value I am determining. So by this process I can remove noise. So I am explaining it again. So you can see the gxy is the corrupted image, and in this case I am adding noise, that noise is eta xy, and in this case I am considering the noiseless image. The noiseless image is fxy, that is the noiseless image, and we have considered the noise has 0 mean value. So that is why the expected value of zi is equal to 0, and also I am considering at every pair of coordinates the noise is uncorrelated. So that means expected value of zi zj is equal to 0, and this the noise effect is reduced by averaging a set of k noisy images. So I am considering k number of images and I am determining the mean value. So k number of images I am considering from I is equal to k, and I am taking the average of this. Now in this case the mean value and the standard deviation of the new image so that the effect of noise is reduced. So first I am showing the new image is, that is the mean g mean xy, and I am determining the mean value, that is expected value I want to see. So if you see, it is expected value of 1 by k, this expression. In place of g mean I am putting this expression, and since 1 by k is constant, so it is taking out, I am taking out from the summation, and after this in place of gi xy I am putting fxy plus noise I am considering, and this it is separated, the fxy is separated from the noise, and already I have considered the noise has 0 mean, so that is why this will be 0 and this value will be k fxy. So ultimately I am getting fxy. So if I take the average of number of images, then I am getting fxy. What is fxy? Fxy is the noiseless image. And also I can determine the standard deviation of the new image. So this is the standard deviation of the new image, and ultimately if I do this calculation, you can see it is 1 by root k sigma eta xy. So if I increase k, what will happen? If I increase k, k means the number of images. If I increase, the variability of the pixel intensity decreases and remains close to the noiseless image value fxy. So that is the case. If I increase k, then the variability of the pixel intensity decreases and remains close to the noiseless image value fxy. So you can see, if I consider number of images and if I take the average of this, then the noise can be reduced. And in this example I have shown the noisy image. The first one is the noisy image. The second one is the averaging of 5 images. I am considering the second result is the averaging of 5 images. Next one is the averaging of 10 images. Next one is the averaging of 20 images. And if you see the next, this image averaging of 50 images, noisy images, and this is the averaging of 100 noisy images. So you can see that the noise is removed because of the averaging operation. The next one is the image subtraction. So already I have explained, because of the image subtraction, I can determine the moving regions. That is called the sense detection. So for medical applications that can be used. Here I am giving one example. So suppose this is my one input image, and suppose I want to determine the locations of the arteries and the veins. So for this I am injecting iodine into the blood stream. So iodine medium injected into the blood stream I am doing. And in this case, if I do the subtraction between these two images, so first image, this is the first image and this is my second image. If I do the subtraction, that is fxy minus hxy, then I will be getting the gxy, the subtracted image I am getting. So you can see the subtracted image, that is the subtracted image is gxy I am getting. That means I can see the locations of the arteries and the veins. And in the next image you can see that portion is enhanced. That portion is enhanced by image enhancement techniques. So you can see the application of image subtraction. Also I can do some logical operations, like I can do AND logical operation, OR operation, XOR operation, NOT operations. Then this operation I can do for image processing. Then in this case the such operations are done on pairs of their corresponding pixels, and in this case I have to consider one real picture and another one is I have to consider a mux for this operation. So first I have to consider the real picture means the image I have to consider, and also I have to consider a machine generated mux I have to consider. So in case of the mux, it is nothing but the binary image consisting only of the pixel value 0 and 1. So this logical operation is performed between the mux and the image. So I can show some examples of these logical operations. So first one is the AND operation. So I am considering the image, the first one is the image, and I am considering the mux is like this. So if I do the AND operation, then in this case the output will be like this. If you see that this portion will be black, the remaining portion will be black. Similarly, if I consider the mux is suppose this mux, and if I do the OR operation, then in this case I will be getting the output image something like this. So I can apply these operations, the logical operations, AND operation, OR operation, all these operations I can apply. And here I am showing one example, another example, that is how to enhance the region of interest. So it is the dental X-ray image, and I am considering the mux, 2 mux I am considering. And in this case what I am doing, the multiplication of 2 images. The first image is, this is the first image, and this is the second image. I am doing the multiplications between these two images. Then in this case you can see the result is this. So what I am getting the region of interest marks for isolating teeth with fillings. So that means in this case I am getting the teeth with fillings. So mainly I am doing the multiplications between the image, the first image and the second image. In the second image I am considering marks. The marks means the region of interest marks for isolating teeth with fillings. So these operations I can apply. Now let us consider the spatial domain filtering operation. So what is the spatial domain filtering operation? I want to explain. So in spatial domain filtering operation, I have to consider the neighborhood operations. So for this I will consider one marks. Suppose if I want to modify a pixel value, then in this case I have to consider the neighborhood pixels, and mainly I have to do some convolution, the convolution operation I have to do, and based on these operations I can consider low pass filter, high pass filter, high boost filter. I can consider this type of filters. Also another important filter is the median filter I can consider. So first I will explain the concept of the spatial filtering, and in this case I will explain the marks, how to do the masking operation, and after this I will explain the concept of the low pass filter, high pass filter, and median filter. I will explain. So in case of the digital image, the frequency means a measure of the amount by which gray value changes with distance. So already you know about the frequency. This is the definition of the frequency, and I may have the low frequency component or the high frequency component in an image, and for this I have the high pass filter or the low pass filters. If I want to select the low frequency component, then in this case I have to apply the low pass filter. If I want to select the high frequency component, the high frequency component in an image is nothing but the edges and the boundaries. And if I consider a low frequency information, that corresponds to the constant intensity or the homogeneous portion of the image. So for the neighborhood operation, I have to consider a filter marks, and I have to take the filter marks from point to point in an image and perform operation on the pixels inside the marks. And based on this, I may have this type of operations. One is the mean operation. So what is the minimum operation? The mean filter. Set the pixel value to the minimum in the neighborhood. That operation I can do. Another operation is the max filter. Set the pixel value to the maximum in the neighborhood. That operation also I can do. And I can do the median operation. So in this case, suppose if I consider neighborhood pixel value is 1, 7, 15, 18, 24. So for this, what is the median value? The median value is 15. So that means the pixel under consideration, that value is replaced by 15. In this case, I am considering the neighborhood operation. So that is, I am considering a marks, and in this marks I am applying these operations, the mean filters, max filter, and the median filter. In this case, I am showing the spatial domain approach, and here you can see fxy is the input image, and t is the transformation. I am doing some transformation, and I am getting the output image. The output image is gxy. T is an operator on the input image. The input image is fxy, and in this case I am considering the neighborhood of xy. So for this I am considering a marks. In this example I am considering the 3 by 3 marks around the pixel is x comma y. That is the center pixel. The center pixel is x comma y. And let us see how to do this operation. So again I am showing this one. I have the input image and I have the output image, and I am considering the neighborhood pixels. So these are the pixels, the neighborhood pixels, and I am considering the marks, and I am getting the output image. The output image is gxy, fxy is the input image, and t is the operation. That is the neighborhood operation I am doing. So marks is similar to this. So it is a symmetric marks, And what is the center pixel of the mux? The center pixel of the mux is x comma y, and that I can consider as a filter. So I have the filter values, the coefficient values, or I can consider as weights of the mux. So this is one example of the mux or the filter. And in spatial domain filtering, what I have to do, I have to put the mux over the image. Suppose I am considering one image Z1, the pixel value is Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8, Z9. And I have the mux, here the mux is, this is the mux. So what are the weights of the mux? The weights are W1, W2 like this, these are the weights of the mux. And what I have to do, I have to put the mux over the image. So corresponding to this pixel, the center pixel, I have to put the mux over the image, that is I am doing the overlapping of the mux with the image. After this, corresponding to the pixel Z5, I am determining the response of the mux. The response of the mux is given by W1 into Z1 plus W2 into Z2, like this I have to determine the response of the mux for the image pixels. So pixels are Z1, Z2, Z3 up to Z9, and in this case I am considering the 3 by 3 mux. The 3 by 3 mux is considered. That is the symmetric mux. This operation again I am showing here. I am considering a 3 by 3 filter. My input image is fxy. I am considering the mux, the 3 by 3 mux I am considering. So this is the filter, and if you see the weights of the filter weights or the coefficients are R, S, T, U, V, W, X, Y, Z. And if I consider the image pixels value A, B, C, D, these are the A, B, C, D up to I, these are the original image pixels I am considering. And already I have explained, so how to do the masking. I have to put the mux over the image, and I have to determine the response of the mux, and that is nothing but V is multiplied with E plus R is multiplied, this is the multiplication. Like this I have to do the multiplication and addition. This process is repeated for all the pixels of the image. Then in this case I will be getting the filtered image. So this concept is called the linear filtering. So if you see this expression here, GMN is the output image, and in this case I am considering the input image is FMN, and I am considering the mux. The mux is given by WM dash N dash. And in this case the summations are performed over the window. And in this case I am considering the filter is the symmetric filter, that is the mux is symmetric mux. Then in this case I can do these operations, that is nothing but you can see it is something like the convolution, because the filter coefficients are multiplied with the pixel values and it is added up. It is nothing but the multiplication and sum up, that is the convolution. And in this case I can show the difference between the linear filtering and the non-linear filtering. I am considering the spatial filtering methods. And in this case if I consider this operation, that means I am determining the response of the mux. A filtering method is linear when the output is a weighted sum of the input pixels. So in this case this is the linear, I am considering the linear filtering. But if I consider this operation, suppose max, the max operation, I am considering 9 pixels because k is equal to 1 to 9, and out of 9 pixels I am determining the maximum pixel, that is the maximum valued pixel. Then in this case this is not a linear filtering, this is the example of the non-linear filtering, because I am just determining the maximum value out of 9 pixels. And already I have explained how to do the filtering, spatial filtering. You can see here I have the input image, and this is the mux I am considering, and in the mux mainly I have to consider the neighborhood pixels, And in this case, how to determine the output pixel? So I have to place the mux over the image, and after this I have to do the spatial convolution. So here you can see this expression is nothing but the spatial convolution, multiplication and the sum up I have to do. Like this I have to determine the filtered image, or maybe output image you can determine. And one thing is that the mux falls outside the edge. Then in this case you can either ignore the edges, the boundary pixels you can ignore, or otherwise what we can do, I can do the zero padding in the boundary pixels, so that I can put the mux in the boundary pixels. These two solutions, one is I can neglect the boundary pixels, that is the ignore the edges I can consider, and if I ignore the edges, the resultant image will be smaller than the original. And if I consider the zero padding, then in this case I will be getting unwanted artifacts. Here I have shown these two cases, one is the zero padding and another one is the I can neglect the boundary pixels I can neglect. Now in case of the linear filtering methods, we have two operations, one is the correlation operation, another one is the convolution operation. So what is the correlation operation and how the correlation is related to convolution? In this case I have shown the same thing, the masking operation. I am considering the mux and I am considering the image is Fij I am considering, and I am considering the mux, that is the kernel matrix I am considering, the kernel matrix is Wij I am considering, and corresponding to this I am getting the output image is Gij I am getting. So in this case what I have to do, I have to put the mux over the image and I have to do the pixel, the multiplication between the pixel value and the weights value of the mux, and after this I have to add all these things. So that means it is nothing but the multiplication and the sum up. So like this, by using this expression you can see, for all the pixels of the image I have to do this operation. For this I have to shift the mux to the next pixel like this, so that I can consider all the pixels of the image. So WST is nothing but that is the mux. This is the correlation operation, and one application of the correlation operation in pattern matching, you can see if I consider, suppose this pattern, the pattern is this, and I want to detect whether this pattern is available in the input image. My input image is this. So if I find a correlation between the pattern and the image, then in this case based on the correlation I can detect whether particular pattern is available in the image or not. In the second example also I can consider the pattern, this pattern I am considering, and by using the correlation I can detect whether this pattern is available in the image or not, that I can detect. That is called pattern matching. And what is the convolution? In the convolution what I have to do, the mux is first flipped both horizontally and vertically. That operation I have to do for the convolution. So mux is first flipped both horizontally and vertically, and you can see here, and after this the operation is very similar to the correlation. Only difference is mux is first flipped both horizontally and vertically, and the rest of the operation is very similar to correlation. But if I consider symmetric mux, the symmetric mux is something like this, then in this case the convolution is equivalent to correlation. So for a symmetric mux the convolution is equivalent to correlation. And in this case I am want to give one illustration of the spatial filtering, and in this case I am considering the low pass filter. Here you can see I am considering the original image, and I am considering the mux, that is the 3/3 mux, for the averaging operation. So if you see the value, it is 111, and mainly it is divided by 9, because I am considering averaging over 9 pixels. So this is the mux corresponding to the averaging filter, that is the low pass filter. And for considering the boundary pixels I am doing the zero padding. So you can see the zero padding I am doing. After this, what I have to do? I have to put the marks over the image and I have to do the convolution. So, you can see in the next slide here, I have to put the marks over the image, and in this case I have to determine the response of the marks corresponding to the center pixel. The center pixel is 7 here. Corresponding to the center pixel, I am determining the response of the marks. The response of the marks is 8.4. After this, what I have to do? I have to move the marks to the next pixel. I have to move the marks to the next pixel, and corresponding to the center pixel is 9 in this case. Corresponding to the center pixel, I have to determine the response of the marks. So, the response of the marks I can determine. So, you can see this is the response of the marks corresponding to the center pixel. The center pixel is 9. So, like this I have to do this operation for all the pixels of the image. So, like this you can see again the marks is shifted and I have to determine the response of the marks. And again you can see I am moving the marks to the next pixel and I am determining the response of the marks. And like this, for all the pixels of the image, I have to do this operation. So, in this demonstration, you can see how to do the spatial filtering, and in this example, I am only considering the low pass filter. So, this operation is very similar to the spatial convolution. So, for all the pixels of the image, I have to determine the response of the marks. And finally, I am getting this image. So, you can see I have the original image and this is the image after spatial averaging that I am getting. So, you can see the result of the averaging filter. So, if I do the averaging low pass filter reduces noise, and in this case if I consider the large filtering window, that means the blurring will be more. In my previous example I have considered only the 3 by 3 marks, and if I consider the large filtering window, then the blurring will be more. So, these are the case, the blurring will be more and the averaging low pass filter reduces noise. And in this case I have shown one example of the averaging filter. Original image is there and I am considering the noisy image and I am having the filtered image, and this is the marks corresponding to the low pass filter, that is the averaging filter. And if I consider the 7 by 7 marks, that is the blurring will be more, because if I consider 7 by 7 marks, this is nothing but I have to divide by 49, and if I consider 3 by 3 marks, that means I am dividing by 9. So, that is why corresponding to the 7 by 7 averaging marks, the blurring will be more. Here I am giving another example. So, original image is this and I am applying 3 by 3 marks, that is the averaging filter I am applying, and you can see the output image, that is the smoothened image I am having. Similarly, I am considering another example. I have the original image and I am considering the 5 by 5 marks and I am having the smoothened image. So, in this case you can see that blurring is more as compared to the previous example. And in this case I am considering the extraction of the brightest objects in an image. So, my input image is this, and after this I am applying 15 by 15 averaging filters, and after this I am just applying the image thresholding technique. So, by this technique you can see I can extract the largest and the brightest object in an image. This is one application of the averaging filter. Next filter I am considering, that is the smoothing filter, the Gaussian filter. In case of the Gaussian filter, if you see, the weights are samples of the Gaussian function. So, I am considering the Gaussian function here, this is a Gaussian function. Corresponding to this Gaussian function, I have the Gaussian mux. Here I am considering the 7 by 7 Gaussian mux. And what about the weights of the mux? Weights are nothing but the weights are the samples of the Gaussian function. So I have the Gaussian function. Only I have to put the value of x and y, so that I will get the weights of the mux. And in this case, if I consider the mux size depends on the sigma, because if I consider height is equal to width 5 sigma, then in this case the area will be 98.76% of the area it will cover. So the mux size depends on sigma, and corresponding to sigma is equal to 3, you can see I am considering 15 by 15 Gaussian mux. So in this case the parameter sigma controls the amount of smoothing, that is, it controls the amount of blurring. So this is one example of the 15 by 15 Gaussian mux. And corresponding to the Gaussian mux, you can see I have the input image. I am considering small sigma, then in this case it is limited smoothing, and if I consider large sigma, you can see more blurring, the strong smoothing. So that the blurring depends on sigma. This is called the Gaussian blurring. Again I am showing the another example. I am considering the Gaussian mux corresponding to this Gaussian function. I am considering the Gaussian mux, and my input image is this, and I am considering two cases. One is the large sigma, another one is the small sigma. So for large sigma the blurring is more as compared to small sigma, and you can see the difference between the Gaussian smoothing and the averaging smoothing. One is the averaging I am considering, another one is the Gaussian smoothing I can consider. That is called the Gaussian blur. The next filter I want to consider, the high pass filter, that is used for sharpening edges. Then in this case what I have to do, how to develop the high pass filter? I have the original image Fn, and if I subtract the blurred image, that is the low pass filtered image, from the original image, then in this case I will be getting the sharpened image. That is nothing but I will be getting the high frequency components. So sharpened image is represented by F high Mn, that is nothing but the high frequency components I will be getting corresponding to the edges and the boundaries. So this is the definition of the high pass filter. So what I have to do, I have to subtract the blurred image, that is the average version of the image, from the original image. Then in this case I will be getting the sharpened image. This operation is important for edge enhancement. So I can highlight the edges. So in this case I have shown the mux corresponding to the high pass filter. So first mux, if you see this one, if I apply this mux, nothing will happen. So that means I will be getting the same image. That is why it is called the identity mux. The original image I will be getting, original image minus the average version of the image, that is the mux corresponding to the low pass filtering, 1 by 9, 1 by 9, 1 by 9 like this. So this is the mux corresponding to the high pass filter. So the center pixel is 8 by 9, and remaining you can see it is minus 1 by 9, minus 1 by 9, minus 1 by 9 like this. So you can see how to get the high pass filter mux. And if I apply this mux, the high pass filter mux, this is the mux corresponding to the high pass filter. You can see here I am considering one input image, and in the input image I am considering the constant the pixel value. If you see the 10, 10, 10 like this value, corresponding to this portion of the image, what will be the response of the mux? If you apply the convolution operation, and if you determine the response of the mux, you can see corresponding to that portion the response is 0. But if I see here that this portion, the pixel value is suddenly changing from 10 to 80, that means that corresponds to edges or the boundaries. So corresponding to that location, if I apply the mux, then you can see the response of the mux is this. So that means corresponding to the high frequency, I will be getting the response corresponding to the high pass filtered mux. So this is the mux corresponding to the high pass filter. And here I am showing one example, and the original image I am considering, that is the original marks I am considering, that is nothing but the identity marks, and this is the low pass filtered marks. And if I subtract the low pass filter marks from the original, I will be getting the marks corresponding to the high pass filter. And if I apply this filter in this image, the image is this input image, then in this case I will be getting the edges. So that means edge sharpening I can do by using the high pass filter, because I am considering only the high frequency components. And in this case you can see, in frequency domain I have shown the first row is the frequency domain corresponding to the low pass filter, high pass filter and the band pass filter. In the second row I am showing the response in the spatial domain. In the spatial domain, this is the response for the low pass filter, this is the response for the high pass filter, and this is the response for the band pass filter. So in this case the center pixel, already you know the center pixel is 8/9. So that means in this case it is a maximum value here you are getting, and in this case it is the averaging operation I am considering. So you can see the concept of the low pass filter, high pass filter and the band pass filter in frequency domain and in the spatial domain. First row is the frequency domain and second row is the spatial domain. The next filter is the high boost filter. So in this case what I have to consider, subtracting an unsharp version of the image from the original image. So that means what I am considering, if you see I am considering the average version of the image, that is nothing but a low pass filtered image, and I am considering the original image is fmn, and I am considering a factor, the factor is a. The a is greater than 1. So what I am doing, the subtracting an unsharp version of the image from the original image. The unsharp version of the image means this is the unsharp version of the image, that is the average image I am considering. And after this you can see this operation, so I can write like this: a minus 1 fmn plus fmn minus f average I can do, and finally I will be getting this expression a minus 1 fmn, that is the original image, and after this f high mn, that is the high frequency image. So if I put a is equal to 1, then in this case this component will be 0. If I consider this a is equal to 1, so this will be 0. Then in this case I will be getting the high pass filtered output. So this is my original image. If I consider a is equal to 1, so if I consider a is equal to 1, then only I will be getting the high frequency components. If a is equal to 1.3, then in this case you can see, if you put this value in this expression, a is equal to 1.3, then in this case corresponding to 1.3, I have the high frequency information as well as the low frequency information. So in this output I do not have the low frequency information, but in the second case you can see, because of a is equal to 1.3, that means I am considering low frequency information as well as high frequency information. If I consider a is equal to 1.5, that means I am considering more low frequency information and as well as high frequency information I am considering. So by applying the high boost filter, I can consider both low frequency information and the high frequency information I can consider. So I am getting the edges, that is sharpening the edges, as well as I am having the low frequency components. And in this case I am showing the same thing, the high boost filtering, fmn is the input image, and I am considering the a factor a cross fmn, and in this case I am considering the average version of the image, and this is nothing but the high boost filter I am considering. So you can see this is my original image, and I am considering, suppose it is a minus 1 I am considering, plus I am considering the blurred version of the image, and I am getting the output is this I am getting, that is the high boost filtering. You can see the difference between the high pass filtered and the high boost filter. So I am considering the original image is this, the first output is the high pass filtered image, I am having the high pass filtered image, and second one is the high boost filter, In the high boost filter, you can see I have the background information along with the edge information. So in the high boost filter, I have the high frequency information as well as the low frequency information. But in case of the high pass filtered image, I have only the high frequency information. That means I have the edges. And in this case, I can show these two examples corresponding to this image. I am applying the high boost filter, and in this case I am considering A is equal to 1.4, and corresponding to this I am getting the output image this. That means I am getting the background information as well as I am sharpening the edges. And corresponding to the second example, I am considering this is the input image and I am considering A is equal to 1.9. Corresponding to A is equal to 1.9, I have the output image. This is the output image. So that means I am sharpening the edges, and also I have the low frequency information. The next filter is the median filter. So median filter is applicable for to remove the salt and pepper noise. The salt and pepper noise is mainly the impulse noises. I have the image. So these pixel values will be affected by the impulse noises, and in this case the high value of this maybe it is 255, or the low value of this noise may be 0. This is something like on and off noise. That is the impulse noise I am considering. And in this case, the median filter operation, what I have to consider? I have to consider a mux, and within this mux I have to consider all the pixels, the neighborhood pixel I have to consider, and this center pixel value is replaced by the median value. So that concept I am going to explain. And one thing, it is important, the median is a nonlinear filter. Why it is a nonlinear filter? So I can show you. Suppose if I take the median AF1 plus BF2, that is not equal to A median F1 plus B median F2. So if you see this one, the median is a nonlinear filter. The median A F1 plus B F2 is not equal to A median F1 plus B median F2. And how to apply the median filter, I can explain you in the next slide. So this is one example of the salt and pepper noise. The salt and pepper noise is nothing but the impulse noises, and it is not affecting all the pixels of the image. Like the in Gaussian noise, the Gaussian noise affects all the pixels of the image. But in case of the salt and pepper noise, it affects only a few pixels of the image, and that is nothing but on and off noise. So my input image is this, and I am considering the salt and pepper noise. Again I am considering, here you can see my input image is this, and I am considering the salt and pepper noise. And in the first case I am applying the averaging operation, and in the second case I am applying the median filtering operation. You can see the difference between the averaging operation and the median filtering operation. So this median filter is very effective to remove salt and pepper noise. And here also I have shown one example, the original image with noise, and in the first case I am applying the averaging filter, that is the output of the averaging filter. In the second case I am considering the median filter. You can see the distinction between these two images. One is the averaging filter, another one is the median filter. So I think the median filter gives better result as compared to averaging filter. And how to apply the median filter? So in this example I am considering one image. My image is this, the pixels value I have shown, and I am considering a 3 by 3 mux, and I have to consider the neighborhood values. The neighborhood value is 115, 1199, 120. These are the neighborhood values, and for these values I have to determine the median value. So for this I have to arrange in the ascending order or the descending order, and after this I have to find the median value. So in this case the median value will be 124. So like this I have to determine the median value. And in this case, in this example, suppose if I consider the 3 by 3 marks, and in this case this pixel is affected by the salt and pepper noise because the value is 255. Then in this case, corresponding to this 3 by 3 window, I have the pixel values. The pixel values are 15, 17, 18, 20, 20, 20, 20, 20, 255. That means I have to arrange in the ascending order, and after this I have to find the median value. So median value will be 20. Then this 255 pixel value, that will be replaced by 20. So this is the concept of the median filter. And in this case I am showing one example. The first one is the input image, and after this I am considering the salt and pepper noise I am considering, and after this what I am considering, if you see, first one is the input image I am considering, after this I am applying the salt and pepper noise, and after this I am applying the 3 by 3 the median filter I am applying. So corresponding to the 3 by 3 median filter I am getting this output. The next one is I am applying the 5 by 5 the median filter, the 5 by 5 median filter I am applying, and corresponding to this I have the output this one. So here also I have shown one example. I have the original image with noise, and I am considering n is equal to 3 median filter, n is equal to 5 median filter I am considering. So you can see the outputs. Then one problem of the median filter is the computational complexity. The computational complexity is in the order of n square. So n means, the small n means the number of pixels in the window. So the computational complexity is very high because I have to find the median value, and in this case the computational complexity is in the order of n square. N is the number of pixels in the window. So that means I have to do n square comparisons to determine the median value for the window. And suppose if I consider the n by n image, then in this case for the entire image, if I want to determine the median value, then my computational complexity n square into n square, that is the computational complexity. Then in this case some algorithms like the quick sort algorithm I can apply because I have to do the sorting. So in this case I can apply some algorithm like the quick sort algorithm I can apply to reduce the complexity, the computational complexity. And again here I have shown the example of the median filter. The first one is the input image, second one I am considering the salt and pepper noise. So all the pixels are not affected by the salt and pepper noise, and after this I am applying the median filter. So this is the output of the median filter image. Finally I want to discuss another filter, that is the bilateral filter. So what is the bilateral filter? So before discussing the bilateral filter, I want to discuss again the mean filter. What is the mean filter? Mean filter blurs the image, removes simple noise, and no details are preserved in case of the mean filter. In case of the Gaussian filter blurs the image, preserves details only for small value of sigma. Already I have explained about the Gaussian filter. And after this I discussed about the median filter. Median filter preserves some details, and it is very good for removing strong noises. Now in this case we want a filter that not only smooth the regions, but it can preserve edges. That means I need the edge information. Also I have to do the smoothing. So for this I have to apply the bilateral filtering. So bilateral filtering smoothed images while preserving edges. That means I have to preserve the edges and also I have to smooth the images. So these two considerations, one is I have to do the smoothing and also I have to preserve the edges. And in this case I have to consider two cases. One is the geometric closeness I have to consider, that means the domain I have to see, and also I have to consider the photometric similarity between the pixels, the neighborhood pixels. So these two considerations I have to take into account. One is the geometric closeness between the neighborhood pixels, and also I have to consider the photometric similarity between the neighborhood pixels. That means I am doing operations for the domain as well as the range. That means I am looking at the domain and the range of the image. So already I have explained. So what I have to do? For this I have to consider the geometric closeness. I have to consider the two pixels can be close to one another, that is occupy nearby spatial location. So that means I have to consider the domain, and also I have to consider the photometric similarity. Two pixels can be similar to one another, that is they have the nearby values. So that means I have to consider the range, the pixel range I have to consider. And in this case what I have to consider, it is a property is nothing but the convolution filter. I have to do smooth images but preserve edges. So that means I am considering the edges, and also I am doing the smoothing of the image. And in this case I have to operate in the domain and the range. For range I have to consider the photometric similarity, and for the domain I have to consider geometric similarity. So you can see the output. One is the Gaussian filter output, another one is the bilateral filter. In case of the bilateral filter, you can see the edges. I am having the edges, and also the image is also smoothened. So combine domain and the range filtering I have to do in the bilateral filtering. And in this case the bilateral filtering is defined like this: Gij, and in this case I am considering the input image. The original image is I, and also I am considering the weight. The weight is Wijkl. I am considering, and Gij is the filtered image. The weight Wijkl, that is the weight I am considering, is assigned using the spatial closeness, that is the geometric closeness I am considering, and the intensity difference, that is the photometric similarity I am considering. One is the geometric closeness, that is the spatial closeness I am considering. Another one is the intensity difference, that is the photometric similarity I have to consider. A pixel located at Ij is denoised using its neighboring pixel located at Kl. And in this case the weight is defined like this. You can see we have two parts. The first part is this, second part is this. So what is the meaning of the first part and what is the meaning of the second part? I can show you in the next slide. So this is the weight. The first part is the domain kernel, you can see, because I have to consider geometric closeness I have to consider. The second part is the range kernel I have to consider, that is the range kernel. The first one is the domain kernel. For the range kernel I have to consider the photometric similarity. So here you can see I am finding the photometric similarity between the pixels, and also I am considering the geometric similarity between the pixels. So you can see the geometric similarity between the pixels. So that means in the bilateral filtering I am considering the domain kernel and also the range kernel I am considering, and that is combined, and after if I combine these two I will be getting the weight. And in this case you can see the bilateral filters with various range of domain parameters value. So I am considering the sigma d, that is the domain parameters value, and also I am considering sigma r, that is the range parameters value I am considering. For different parameters you can see the output images. That means I am considering both range and the domain filtering in the bilateral filters. So in this class today I have discussed about the spatial filtering. First I discussed about the concept of the masking. After this I discussed about the concept of the low pass filter and the high pass filter and the high boost filter. After this one nonlinear filter I discussed, that is the median filter I have discussed, and finally I discussed the concept of the bilateral filtering. So in the bilateral filtering we considered the domain filtering and the range filtering. So this is about the spatial filtering. In my next class I will discuss about the concept of frequency domain filtering. In frequency domain filtering I have to modify the Fourier transform of the image. So that concept I am going to discuss in the next class. So let me stop here today. Thank you.